Hi everyone, this is Mrs. J. Today we are going to learn how to solve exponential equations, but first please pause the video and give this warm-up a try. Okay, go ahead and check your work here. So if you rewrite 20 as 2 times 2 times 5, you'll see that log base 3 of 2 and log base 3 of 5 are values that we are given decimal approximations of. So I can use my product property to expand it, and then I can use the approximations I'm given. For log base 3 of 25, I can rewrite 25 as 5 squared and use my power property, or rewrite it as 5 times 5 and use my product property again. And for log base 3 of 5 over 4, I can write it as 5 over 2 times 2. Now remember, anything from a denominator gives you a negative exponent. So both of these, a negative logarithm. So both of these logarithms should be subtracted. All right, so today we are going to be focusing on solving exponential equations, which are equations where the variable is in the exponent. So depending on how your equation looks, you can try one of these two methods. For some problems, this won't work for everything. You can actually rewrite the expressions so the bases are the same. So if you have two exponential expressions equal to each other, see if you can make the bases are the same. Because by logic, if you have two expressions that are equal, two exponential expressions that are equal, and the bases are equal, by logic, the exponents must also be equal. So that's one thing you can look for. Now this won't always be possible. So if it's not possible, we'll go on to method 2, which is to first isolate your exponential term, and then we will take the log of both sides. And there's a few different routes you can go from here, but once you do that, you can use your properties of logarithms to rewrite and finish solving. Okay, let's give this first one a try together. So here I have an expression equal to an expression, and if you look at the bases, I see that these numbers are related. I have 100 and 1 over 10. These are both powers of 10. So I'm wondering if I can write them both to have base 10. So I know that 100 I can rewrite as 10 squared. And I know that 1 over 10 I can rewrite as 10 to the power of negative 1. And now if I clean this up a little bit, I multiply my exponents. Make sure here I'm distributing the negative to both pieces of my exponent, so negative x plus 3. Now I have two terms. They're equal. Their bases are equal, so just by logic, their exponents must also be equal. So from here, all I need to do is set my exponents equal to each other and finish solving. And I get x equals 1. For these types of problems, you don't have to check your work. Of course, you are always welcome to plug in the answers to see if your answers are correct. All right, let's look at this next one. So here I see I have a base 8 exponential term and a base 2 exponential term. So I know that both of these are powers of 2. This one is just already base 2, and I can rewrite 8 as 2 cubed. I don't need to rewrite the right side of my equation, which is nice. And then I'm going to multiply the exponents, making sure to distribute, so it becomes 6x minus 3, and 2 to the power of 4x minus 4. And again, if the expressions are equal and the bases are equal, the exponents must also be equal. So I can just set the exponents equal to each other. And I'm going to subtract 4x from both sides and add 3 to both sides. So x is negative 1/2. So here you can see the strategy of, again, rewriting the terms so the bases are the same. All right, go ahead and pause the video and give this one a try on your own. Go ahead and check your work here. So for the first one, you can rewrite 81 as 9 squared and 1/9 as 9 to the negative 1. please don't forget to distribute this exponent to the x and the positive 3. And for part B, if you rewrite 25 as 5 squared, remembering to distribute, so it becomes 4x plus 2, then the bases match. All right, let's look at some problems where we aren't able to use that first method. So here we have 3 to the power of x equals 8. There's no way to rewrite 8 as a base 3 number, so we need to use that other strategy. Then again, there's a few different ways you can use this strategy. So once the exponential term is isolated, what we can do is we can take the log of both sides. And we can just take the common log of both sides every time, and that will work. And then from here, we can use our power property, and I can move that exponent out front. So x times the log of 3 equals the log of 8, and then all I have to do is divide both sides by the log of 3. The log of 3 is just some value, so you treat it just like a normal number. We can multiply or divide it to both sides just like any other number. So our final answer is the common log of 8 divided by the common log of 3. Now this would be considered an exact answer. So exact answers will often have a logarithm in them. So you see in the directions that we were also asked for a decimal approximation rounded to the nearest thousandth, which is 3 decimal places. So then you would type those into your calculator, common log of 8 and common log of 3, and you could get the decimal approximation. X is approximately 1.893. So this is one way you can use this strategy. You can just take the common log of both sides. In this one, I'm going to do it slightly differently. So first, we do need to isolate our exponential term. So I'm going to add 4 to both sides. And again, there's no way to rewrite these terms so they have the same base. But this time, instead of taking the common log of both sides, I'm going to take the log base 2 of both sides. As long as you're doing the same base logarithm of both sides, it's completely legal. So why would I pick log base 2? Well, here we have this inverse property of logarithms, where if the base of the logarithm and the base of the exponential term match, they essentially cancel each other out, and all you have left is just x. So we have x equals log base 2 of 7. So this would be an exact answer. Now, to get a decimal approximation from this, we would need to rewrite it using our change of base formula. So I'll do this with common logs. I'll do the common log of 7 over the common log of 2. And then this we can plug into our calculator to get our decimal approximation. And we get about 2.807. So you'll see that we still end up having to rewrite it with common log. So sometimes it's just a little more efficient to just solve it in this way, where you just take the common log or the natural log of both sides and then just use your power property. But some people prefer taking a log with a base that matches the base of the exponential term. Either way, you will get answers that are equivalent. So it's really what you are more comfortable with. All right, here's the last you try, so please pause the video and give it a shot. All right, go ahead and take a look here. So I did slightly different methods for each one. For the first one, I chose to do log base 4 on both sides just to match the base of my exponential term. And then this just simplifies to x. So log base 4 of 17 is an acceptable answer. Common log of 17 over common log of 4 is acceptable. Natural log of 17 over natural log of 4 is acceptable. And if you have this form, you will need to rewrite it to get that decimal approximation. Then for part B, please make sure you divided both sides by -3 first. You do need to isolate your exponential term. Then for this one, I just took the common log of both sides. I used my power property to move my exponent to the coefficient spot. And then I divided both sides by the common log of 5. So this would be my exact answer, and this is my decimal approximation. All right, that is all for today's lesson. Thank you so much for watching.